Hello guys, how you doing? Today is the sixth session of instructing for chapter 3 of fluid mechanics 1. The title is Example of Use of the Bernoulli Equation. So follow me with the whole video. So as I told you, today's subject is titled as use examples of use of the Bernoulli equation, which is from section 3.6 from chapter 3 of fluid mechanics 1. Before going on instruction, I'm willing to introduce myself. My name is Amir Raza Talakat, and you can email me through address of amirrazatalakat@gmail.com. Please don't hesitate to ask any questions about your problems or fluid mechanics. I try my best to give you the answer as soon as possible. As you know, we have already been through many principles of Bernoulli equation, which is addressed as P1 plus 1 over 2 rho V1 to power 2 plus gamma Z1 is equal to P2 plus 1 over 2 rho V2 to power 2 plus gamma Z2, which is applied in based on the assumptions of steady, inviscid, incompressible, and flowing in a horizontal line. One of the oldest equations in fluid mechanics about the Bernoulli equation is about a large reservoir. In this session, we're gonna see the examples of Bernoulli equation, which first of them is the reservoir from principle of free jets. As you see, when we apply the Bernoulli equation between point 2 and point 1, we have following assumptions and following calculations. Z2 is connected to the atmospheric side, so the pressure at this side is 0. The origin is point 1, so the origin is also in point 2, so Z2 is 0 as well as the P2 is 0. As the flow is not having any motion at point 1, so the velocity of point 1 is 0. As long as the P2 is 0, we're having the free jets. So the whole equation from Bernoulli equation applied between point 1 and 2 is going to be regarded as this, which is gamma H1 is equal to 1 over rho V2 to power 2. The subscription are not mentioned here. Having the velocity, we can do the calculations and have the equation 3.18. We can also apply the Bernoulli equation between point 2 and 3. As you see, the velocity of point 3 is 0 because it's coming to the downside and it's coming at rest. Z1 is having the elevation as h minus L from point 2. And so the pressure at this side is going to be gamma H minus L. And gamma multiplied H minus L. As long as we are having the free jet at the point 2 side, point 2, the pressure is going to be equal to the surroundings, as it's going to be equal to 0. One of the term for this for point 2 is that it's having incompressible fluid jet, so its pressure is going to be equal to the surrounding side. Another thing is that we can apply we can identify the situation between point 2 and 4. You know, uh, as long as point 2 and 4 are in the same line, so the pressure is not really considerable, since we are having the radius equal to infinity. Uh, and also we are having no components of weight force, so the total pressure in point 2 is equal to P4 equal to 0. If we apply the Bernoulli equation between point 1 and point 5, we can go through this. But we have to identify the h as h plus h capital, because we are moving from here to here. The basic concept between point 2 and 4 is happening in the nozzles, as we are having the free jets. Going to the second slide. Yeah. As you are already aware of Bernoulli equation, the phenomena is such that the potential energy is going to be converted to the kinetic energy, based on having the assumption of viscous or friction effects are negligible. When we are moving from from top to the downside, reaching the point 1, we are having a pressure which is gonna increase gradually from top side to the bottom side. So in here, pressure is greater than here, and the pressure in here is greater than here. If this side be so small than this height, we can have the average velocity at the center. So the velocity in point 1 is so smaller than point 2 and smaller than point 3. So in here we are having another concept of free jets. As you see, we have tips over here at point 1 and point 3 either. This means that we are having a stagnation point happening, as I told you in the previous session. Reaching here, as we have a tip, the velocity goes to the pressure goes to the climax, as it's confronting the tip. The pressure is gonna increase gradually till it reaches to the center line. So in the center line, we are experiencing the sharpest amount, the biggest amount of pressure, as well as the pressure gradient happening in the streamline. So the pressure first is 0 in here, and then is gradually increasing till it reaches to the center line. If we have dg in here smaller than dh, we can consider the uniform velocity distribution. The main reason why we have the pressure rise in here, the pressure equal to 0, I was mistaken. The pressure in here and here are 0, is owing to the velocity increase. But the gradient is happening based on the curvature, as we are as it's having the curve to reach to the streamline. This figure can help us to have the constant multiplication to the velocity equation, as well as the pressure, in order to have it proper in a proper amount. it is based on the geometry that it can be helpful to us. The second concept about application of Bernoulli equation is regarded to syringe application, which is happening from confined fluids. As you know, in syringe, as the flow comes into the confined area, that amount of flow should be going outlet. So the amount of inlet should be equal to the amount of outlet, which is this concept is termed as continuity equation. We're going to go through the details in chapter 4 and 5, but in here we just need the simple form of continuity. The simple form is derived as this: m dot is equal to density multiplied by the volume flow rate. Volume flow rate is the multiplication of velocity going passing through the corresponding cross-sectional area in an interval time, in a time interval, which is happening like this. This part is a volume flow rate. The mass flow rate itself is, as I told you, density multiplied by volume flow rate. We can write the mass flow rate as rho VA, which is density multiplied by velocity multiplied by the corresponding cross-sectional area. As you see, in order to have the constancy between inlet as well as the outlet flow rates, the equation should be happening as this: V2 is equal to A1 V1 divided by A2. This means that if we have cross-sectional area at part A twice of part 2, we have a twice velocity at the outlet. This is the main fact in order to have the continuity equation. So in this example, which is we are having 3 examples actually, which are 3.7 about flow from a tank and the gravity, examples 3.8 and 3.9, which are flow from a tank regarding the pressure, and flow in a variable area pipe respectively. I'm gonna illustrate 3 of them in a written text, so follow me with it. So welcome guys to this part, which is problem solving of example 3.7, titled as flow from a tank regarding the gravity, from chapter 3, section 3.6. If I let's just recheck it again. Yeah. So the question is, a stream of refreshing beverage of diameter d small d is equal to 0.01 meter. So we have the d small as 0.01 meter. Flows steadily from the cooler of diameter 0.2. Capital D is equal to 0.2 meters, as shown in figure E3.7a and b. Determine the flow rate Q from the bottle into the cooler if the depth of the beverage in the cooler is to remain constant at H equal to 0.2 meters. So, as we are regarding the steady, inviscid, incompressible flow, we can have the Bernoulli equation. So, inviscid, incompressible, as well as the steady flow. So Bernoulli equation checks between point 1 and 2. P1 is equal plus 1 over 2 rho V1 to the power 2 plus gamma Z1 is equal to P2 plus 1 over 2 rho V2 to power 2 plus gamma Z2. P1 and P2 are connected, both are connected to the atmospheric pressure, so they are 0. And we have Z2 as the origin, and the Z1 is H. So we can have it as this: 1 over 2 rho V1 to power 2 plus gamma and GH plus is equal to 1 over 2 rho V1 to power 2. And we can have it as this: it's gamma H here. Then we can divide the rows from both sides, and we can have this as 1 over 2 V1 to power 2 plus GH is equal to 1 over 2 V2 to power 2. Although the liquid remains constant at altitude of H, there is an average velocity V1 cross section of point 1. So in point 1 we can have the average velocity because of the flow from the tank. As the tank is getting drained, the flow, the velocity profile at the outlet can be regarded as the uniform, and we can have the average velocity. This means that we can have the continuity equation from equation 3.19, which is Q1 is equal to Q2, which means A1 V1 is equal to A2 V2, which is P over 4 D2 D to power 2 V1 is equal to P over 4 D small to power 2 V2. We can have the V1 as this: D over D capital to power 2 V2. Having this equation, which I'm going to name it as number 3, this is number 2, and also this is number 1. Combination of equations 1 and 3, we can have the V2 as square root of 2GH over 1 minus D over D capital to power 4. We have this as 0.2, we have it as 0.01, H is 0.2, and G is 9.81 meter per square second. And from this equation, we can have the Q, it's the total Q, as A2 multiplied by V2, which is P over 4, 0.01 to power 2, 1.98 meter per second, which is this. We can have the flow rate as 0.56 multiplied by 10 to power minus 4 cubic meter per second. So, welcome guys to this section, which is problem solving of example 3.8, titled as flow from a tank according to pressure, from section 3.6 of chapter 3. The question is, air flows steadily from a tank through a hose diameter as a capital D of 0.03 meters and exits to the atmosphere from a nozzle of diameter D small as 0.01 meters, as shown in figure E3.8. The pressure in the tank remains constant at the 3 kilopascals gauge. P is equal to 3 kilopascal gauges. gauge, excuse me, G. And the atmospheric conditions are standard temperature and pressure. Standard condition. So we have to find out the flow rate and the pressure in the hose. So as we are again considering inviscid, incompressible, as well as the steady flow, the Bernoulli equation checks. So we can apply it between 3 points ahead of each other. 1, 2, 3, which are P1 plus 1 over 2 rho V1 to power 2 plus gamma Z1 is equal to P2 plus 1 over 2 rho V2 to power 2 plus gamma Z2 is equal to P3 plus 1 over 2 rho V3 to power 2 plus gamma Z3. Between 0.2 and 1, we can have it as this. P2 is equal to P1 minus 1 over 2 rho V2 to power 2. Because we're in the same elevation, this checks. And also we are starting from 0 velocity to going forward. This is 0. And then we can have the other things. It is equation 1. The density of air in the tank is obtained from the perfect gas law. Pay attention, guys. This is the main reason why it has stated the standard condition. So we can have the density as P1 over RT1. This is this is 3 plus 101 kilonewtons per square meters, owing to the fact that we have the absolute pressure. It's absolute. R is equal to 286.9 Newton meter per kilogram degree of Kelvin. This is 15 plus 273 degree of Kelvin. So we have the density as 1.26 kilogram per cubic meters. Then we can find out the V3, which is square root of 2 multiplied by 3 multiplied by 10 to power 3 newtons per square meter over rho, which is 1.26 kilogram per cubic meter. We have the V3 as 69 meter per second. This is the same for the equation that we have applied here. From this section, we can figure out the V3 either. This is the main reason why we have the V3 here. From the continuity equation for point 3, we have the total Q as A3V3, which is P over 4 D to power 2 V3. This is 0.01 to power 2. This is 69. So we have the flow rate as 542 cubic meters per second. Between 0.2 and 3, we have the same thing. which we can gain V2 from A2, A3, V3 divided by A2. This is going to be d over d capital to power 2 V3, which are 0.01 divided by 0.03 to power 2 multiplied by 69. Then we can have the V2 as 7.67 meter per second. The V3 is corresponding to P3. P3. Yeah. The pressure, the velocity of point 3 is equal to square root of 2 pi 1 divided by density. Because the P3 is the free jet. From equation 1, from here, we can have the pressure at point 2. Let me just see what we have done. Yes. This is for this. So the pressure at point 2 is equal to 3 multiplied by 10 to power 3 minus 1 over 2 rho, which is 1.26 multiplied by V2, which is 7.67, which is going to be 2,963 Newton per square meters. So, welcome guys to this part, which is about problem solving of example 3.9 about flow in a variable area pipe from section 3.6 of chapter 3. The question is, water flows through a pipe reducer as shown in figure E.3.9. The static pressure at 1 and 2 are measured by the inverted U-tube manometer containing oil of a specific gravity Sg. So less than 1, which is less than 1, and it wants us to determine the manometer reading H. So as you see, we are considering again incompressible, steady, and inviscid along streamline flow. This all means we can have the Bernoulli equation checked, applied. Between point 1 and 2, we have it as this: P1 plus 1 over 2 rho V1 to power 2 plus gamma Z1 is equal to P2 plus 1 over 2 rho V2 to power 2 plus gamma Z2. And also we can write the continuity equation between point 2 and 1. And also we have this A1 V1 is equal to A2 V2. By combination of these two equations, this and this, we can have P2 minus P1 is equal to gamma Z2 minus Z1 plus 1 over 2 rho V2 to power 2 multiplied by 1 minus A2 divided by A1 to power 2. So the pressure difference can also be calculated from the chapter 2 about manometers, which we can have it as this: P1 minus gamma Z2 minus Z1 minus, as we're getting up, gamma L minus gamma H plus Sg gamma h as we are coming down plus gamma L, which we can have the P2. So as a result, we can have it as this: gamma Z2 minus Z1 plus 1 minus Sg gamma H. So putting it at here, we can have it as 1 minus Sg is multiplied by gamma H is equal to 1 over 2 rho V2 to power 2 multiplied by 1 minus A2 to A1 to power 2 totally. As we have it as we have V2 as Q over A2, we can have it as this, which for H is equal to Q over A2 to power 2 multiplied by 1 minus A2 over A1 to power 2 over 2G minus 1 SGs. Welcome back, guys, to this section, which is a part I like best. As I already told you in the last two sessions, which was about physical interpretations of section 3.4, at last slide I demonstrated that when an aircraft is going to climb up, the air rolls are going to be varying in this angle. When the angle is like this, the velocity passing over is really high, so the pressure in this side is really low. Vice versa, the pressure in this side is really high and the velocity is very low, so the aircraft is going to climb up. But the differences of velocity in terms of pressure for the gases are really considerable. When the cavitation is happening, the cavitation is illustrated in the chapter 2. It means that the pressure drops down such that it's going to be getting near to the vapor pressure. As it comes to this status, the boiling is going to be happening, not regarding the temperature. This means that the pressure is gonna climb up in an extraordinary trend. In this case, if we haven't got any probable designs, the whole thing is going to be collapsed. As you see in here, as the flow is gonna getting near to this side, the pressure is gonna be coming down, getting near to the vapor pressure. So the boiling is getting happening. Another example of this phenomena is having the hissing sound around the windows in the winter or fall or any situation that the wind is flowing. This is the basic concept of cavitation that's happening in our daily life. As I told you, when the bubbles are being created in a cavitational phenomena, if we haven't got any appropriate designs, as I told you, the collapse is going to be happening. So we have to take care about any hypothetical situation that might be happening during pressure decrease. The pressure amount is such that is as large as 100,000 psi, which is 690 megapascals. This is most critical situation that might be happening in the industrial equipment, most likely in power plants or refineries. In order to in order to grasp it appropriately, I'm gonna uh, solve the problem of example 3.10, which is about siphon and cavitation in a written text. So follow me with it. Welcome guys to this part, which is about problem solving of example 3.10 of siphon and cavitation from section 3.6 of chapter 3. The question is, a liquid can be siphoned from a container as shown in figure E3.10a, provided end of the tube, point 3, is below the free surface in the container. Point 1 and the maximum elevation of the tube, point 2, is not too great. Consider water of 60 degrees of Fahrenheit being siphoned from a large tank through a constant diameter hose as shown in figure E3.10b. The end of siphon is 5 feet below the bottom of the tank, and the atmospheric pressure is 14.7 psi. Of atmospheric is 14.7 psi absolute. Fine, the question wants us to determine the maximum height of the hill h over which the water can be siphoned without cavitation occurring. So, as we are, as you know, we are considering inviscid, steady, incompressible, along a streamline flow, which means we can have the Bernoulli equation applied. Between point 1 and 2, we can have it as this: P1 plus 1 over 2 rho V1 to power 2 gamma Z1 is equal to P2 plus 1 over 2 rho V2 to power 2 plus gamma Z2. And also between point 3, which is going to be equal to P3 plus 1 over 2 rho V3 to power 2 plus gamma Z3. V1 is equal to 0 as we are taking it as a large tank. And also the P1, we are having an open tank. And also the P of point 3 as we are having the free jet. It is also 0. And furthermore, as we are having the same areas between point 2 and 3, we can have the V2 equal to V3. So V3 is going to be calculated as a square root of 2g Z1 minus Z3, which is minus 5 because it's below, it is 15, and the g is 32.2 feet per square second. We're going to have the V3 as 35.9 feet per second. So we can have the pressure of point 2 if we have this part over here as P1 plus 1 over 2 rho V1 to power 2 plus gamma Z1 minus 1 over rho 1 over 2 rho V2 to power 2 minus gamma Z2. So we can have it as this. Gamma Z1 minus Z2 minus 1 over 2 rho V2 to power 2. As we are taking the water at a temperature of 60 degrees of Fahrenheit, going to the table B.1, we can at temperature equal to 60 degree of Fahrenheit, we have the pressure of 0.256 psi absolute. Why we have gained this? In order to prevent the cavitation, we have to calculate it for incipient cavitation, which means we have to take it as absolute to gain the minimum pressure. In order to have P2, we can have it as this, 0.256 minus 14.7, as we have the P atmospheric equal to 14.7. PSI absolute, minus P of atmospheric. We can have it as PSIG. So it is equal to minus 14.4 psi gauge. This means that if we take it here, minus 14.4 psi pound per square inches multiplied by 144 square inches is equal to 1 square feet, is going to be equal to 62.4 pound per square cubic feet, 15 minus h, minus 1 over 2, 1.94 slugs per cubic feet, multiplied by 35.9 to power 2 feet per second, which means we have h as equal to 28.2 feet. Welcome guys to this section, which is about application of Bernoulli equation in flow rate measurement. As you know, ideal situation is not really happening in real world for Bernoulli equation assumptions. But in here, we have three typical instruments that can be helpful in a flow rate measurement for Bernoulli equation. First of all, we have orifice, nozzle, and venturi. If we apply the Bernoulli equation for between point 1 and 2, we can have it as this, as we have no elevations. Where once we have a considering a continuous situation, we have this equation either, which flow rate is equal to corresponding cross-sectional area multiplied by the velocity. These three items are really applicable in piping construction as well as the instrument analysis, owing to the fact that they are connected directly to the flow area, so they can give us whole information. Combining this and this equation, we can have the flow rate as equation 3.20. If we increase the area such that A1 is really larger than A2, we can eliminate this part and have it as Q is equal to A2 square root of 2 multiplied by P1 minus P2 totally over density. However, the actual flow rate is depending on the geometry that we are considering. The variation between the actual flow rate and the theoretical flow rate is something between 2% as large as 40% based on this graph that's happening over here. Let me bring it near to give it to you properly. In here, we are having a square root of this equation as a graph. So we have reached example 3.11, which is about Venturi meter. I'm going to solve it to you in a written text, so follow me with it. So guys, here we have problem solving of example 3.11, which is about Venturi meter from section 3.6 of chapter 3. Kerosene, which is having SG. The question is about this I'm going to talk about. The kerosene having SG of 0.85 flows through a Venturi meter shown in figure E.11a with the flow rates between 0.005 cubic meter per second and ultimately 0.05 cubic meter per second. The question is to determine the range in pressure difference P1 minus P2 needed to measure these flow rates. So, as we are having, again, steady, inviscid, incompressible, along streamline flow, we can use equation of 3.20, through which we can have P1 minus P2 is equal to Q to power 2 rho multiplied by 1 minus A2 over A1 to power 2 totally divided by 2 A2s. We can have the rho as Sg multiplied by rho of water, which is 0.85 multiplied by 1000 kilogram per cubic meter, which is going to be 850 kilogram per cubic meter. As we have to determine the A2 over A1, we can have it as D2 over D1 to power 2. Totally, the proportion is going to be D2 over D1, which is 0.06 divided by 0.01. If I get it correct, no. There's a 0.1 here, which means 0.6. Totally, it is going to be 0.36. Q is going to be for the first one 0.005, and for the second one is going to be 0.05. And the A2 is equal to pi over 4. A2 is equal to 0.06 to power 2. So for the first option, P1 minus P2 is going to be equal to 1.16 kilopascals, which is 1116 Newton per square meters. For the second one is going to be equal to 116 kilopascals, which is going to be 1.16 multiplied by 10 to power 5 Newton per square meters. Welcome guys to this section, which is about another application of Bernoulli equation in open channels, such as flumes, irrigation, or detaches. We can have a slice gate, which is in a sharp crested weir. as we have considered the assumptions of steady, inviscid, incompressible flows. The slice gate is going to be separately studied in chapter 10, but in here we're just considering as application of Bernoulli equation. As you see in here, the flow rate Q is the function of water depth, which is Z1, width of the gate, which is B, and the gate opening A. If we apply the continuity equation, we can have it as this. And first of all, before taking this step, we have to take the considerations between point 1 and 2 by applying the Bernoulli equation. P1 and P2 are directly connected to the atmospheric side, so they are totally zero. And the elevation is happening as Z1 to Z2. Doing the calculation and apply all the amounts, we can reach to equation 3.21 for flow rate, as they are as I told you, the flow rate is a function of the width, the opening gate, and the height of here. If we consider this height really larger than Z2, we can have it as this. Furthermore, we can apply the Bernoulli equation between point 3 and point 4 either, but the best situation that is happening for us in order to validate our considerations is happening between point 2 and point 1. There's another point that I want to tell you about. The proportion of Z1 to A to Z1, excuse me, is somehow having effect on our calculations, owing to the fact that the geometry in here is really important. If the value of A to Z1 is between O and 0.2, it's having approximately the value of 0.61. Excuse me. The best situation is happening, but going larger than 0.2, this proportion is gonna increases rapidly. Let me have example 3.12, which is about slice gate, solve for you in order to give you the demonstrations appropriately. So follow me with the written text. So, welcome guys to this part, which is about problem solving of example 3.12 about slice gate of section 3.6 of chapter 3. The question is, water flows under the slice gate shown in figure E3.12a. It wants us to determine the approximate flow rate per unit width of the channel, Q over B. We can use equation 3.21 as we are considering steady, inviscid, incompressible, excuse me guys, incompressible along streamline flow. So we can have it as this: Q over B is equal to Z2 square root of 2G Z2 minus Z1 minus Z2 divided by 1 minus Z2 over Z1 to power 2. As you know, Z1 is 5 A is equal to 0.8. A divided by Z1 is equal to 0.8 divided by 5, which is going to be 0.16, which is less than 0.2. So we can assume the contraction coefficient is approximately equal to 0.61. So we can have Z2 as contraction coefficient multiplied by A. We can have it as 0.61 multiplied by 0.8, which is going to be 0.488. So this is 0.488. This is 0.8. Excuse me, this is 5 Z2 over Z, and we can have the same amounts in here. Then in doing the calculations, we can have the flow rate per unit of width as 4.61 square meter per second. Welcome back, guys. One last thing about the flow rate measurement application of Bernoulli equation is about the weir. There's a typical rectangular sharp crested weir in here, which we can apply in which we can apply the Bernoulli equation between point 1 and point 2. As you see, the weir plate is dependent to the weir height, which is PW, and also the width of the channel B, and also the head H. When the flow is having motion is moving from point 1 to point 2, it's going out. So it means that we have atmospheric pressure at this side, which is increasing in this part until it reaches along the streamline, in the middle of the streamline, and then increases again, and then it decreases. The distribution of pressure as well as the streamline for velocity profile gives us the complex equations, which through which we can have the flow rate as C1HB square root of 2GH capital. If we do more calculations, we can have the flow rate as function of h to the power 3 over 2. The constant C1 is not really known coefficient. It's hypothetically gained based on the calculations in the laboratories by accurate values. Everything is all done, yeah. So we have the last example, which is about the weir, example 3.13. I'm going to solve it to you through the written text, so follow me with it. So welcome, guys, to the last problem solving of this session, which is about example of 3.13, about the weirs of section 3.6 of chapter 3. The question is, water flows over a triangular weir as shown in figure E.13. It wants us to figure out a simple analysis using by using simple analysis of Bernoulli equation and to determine the dependence of flow rate of the depth h if the flow rate is q0 when h is h0, and estimate the flow rate when the depth is increased to h equal to 3h0s. We can just illustrate something like this with the assumption that the flow is steady. As you know, we have the steady, inviscid, incompressible, along streamline flow. So we can have the Bernoulli equation applied. which is about the wears. From equation 3.18, we already know that as the velocity is so high at the upside, we can have the velocity as square root of 2gh, which is 2gh capital. And the flow area for the depth of the h is equal to h multiplied by h tangent of half of angle. So combination of these two ideas for the triangular, this is the area for triangular notch. So we can have it as the flow rate can be AV, so it is equal to H2 tangent of angle half multiplied by C2 square root of 2GHs, which is gonna be equal to something like this: C2 tangent of angle half square root of 2 h to power 5 over 2. If we have it as 3h over h, which is 3h to power 5 over 2, or h 5 over 2, it is going to be equal to 15.6. So guys, this is the end of this session. I hope you have grasped the fundamentals and principles correctly. And I'm really happy that you have accompanied me till this moment of the video. Once again, I ask you to don't hesitate about asking your questions in the comment of the video or in the email. I try my best to give you the answers as soon as possible. Most importantly, subscribe the channel in order to get the notification of upcoming instructional sessions. Take care of yourselves. I bid you all farewell. See you in the next session.